Yeah, okay. Hi, welcome back to the afternoon session for this day. I'm Varun and I'll be moderating this session. So right now we have Varinder Singh from ICTS to talk about thermodynamic uncertainty in major heat engines. So please take over.
Okay, thank you. Hello everyone. So I am Varinder Singh. So today I am going to talk about my work on thermodynamic uncertainty relation in major heat engines. So first of all, I want to thank the organizers for having me here. So here is a brief outline of my talk. So I will start with the basic concept of Carnot cycle. Then I will discuss briefly about the power efficiency trade-off in thermal heat engines. Then I will define thermodynamic uncertainty relation, and then I will discuss the validity of this thermodynamic uncertainty relations in major heat engines. So back in 1824, Sadi Carnot, a French engineer, introduced the concept of Carnot cycle. So it is an ideal reversible cycle which consists of 4 branches, 2 adiabatic and 2 isothermal. So here is a pictorial depiction of Carnot cycle for ideal gas. So the efficiency of the Carnot engine is given by this formula. Eta is equal to 1 minus Tc by Th. So this is the temperature of cold reservoir. This is the temperature of hot reservoir. So this is a universal result because this doesn't depend on the parameters of the system. So it's a universal result and it puts theoretical upper bound on efficiency of all heat engines working between 2 thermal reservoirs. But although it works at the maximum efficiency, but it is horribly impractical because it generates 0 power output. So it's not a practical heat engine. So real heat engines, they should operate with finite power. So which actually makes them irreversible. And this amount of irreversibility can be quantified by entropy production. So actually, for steady state heat engines which are coupled to 2 thermal reservoirs, so this is the first law of thermodynamics in the steady state, so which accounts all the fluxes in the system. So this is the flux from hot reservoir, this is flux from cold reservoir, and this is the power of heat engine. So in the steady state, this is equal to 0. And again, this is the formula for entropy, a rate of change of entropy. In the steady state, rate of change will be 0 because system is at steady state. And these are the entropies which are exchanged with hot and cold reservoirs, and this is the spontaneous entropy production. So which doesn't exchange with anything, it spontaneously actually produce inside the system. So now the efficiency of a heat engine can be simply written as power over like heat flux from the hot reservoir. So this is output, this is the input, and by using using simple these 2 formulas expression for the entropy, we can arrive at this equality. So that eta equal to efficiency of the engine, eta C minus Tc by sigma over QH dot. So here sigma is the entropy production. So it we can see that due to the positive entropy production, efficiency of the engine is smaller than Carnot efficiency. So it says that usually real heat engines, they cannot operate at Carnot efficiency. So it has been observed that there is a trade-off between efficiency and power in all thermal heat engines. So here is a pictorial depiction. So in x-axis I have plotted efficiency, in here I have plotted the power. So as we can see that from this diagram, at 0 power 0 efficiency, then at maximum efficiency 0 power. So this is the point where efficient power is maximum. So this point is efficiency at maximum power. From this figure, we can conclude that heat engine should operate in this area, just right to this vertical line. Okay, if you operate heat engine in this area, this will be inefficient. So again, and the question is it possible to beat this trade-off between efficiency and power in heat engines? And moreover, the most important question is, can you operate a heat engine with maximum efficiency at finite power? So the answer, so I will in a couple of moments I will provide the answer, but before that I would like to introduce thermodynamic uncertainty relations. So now actually thermodynamic uncertainty relations deals with entropy production and fluctuations. Now in small systems, stochastic systems or small quantum systems, due to their small size, they are subjected to strong fluctuations, so which ultimately affects their precision. And as I already mentioned that when you operate heat engines with finite power, so there is entropy production. So this thermodynamic uncertainty relation, it represents a trade-off between the rate of entropy production and the precision of the this heat engine. So precision is defined by the relative fluctuations in power output of the heat engine. So this is the thermodynamic uncertainty relation, this inequality, and it was actually introduced back in 2015 by Brato and Seifert, and then it was proved by using the formalism of large deviation theory in 2016. So these are applicable to our system which are driven to non-equilibrium steady state and obeying continuous time Markovian dynamics. Now this inequality provides more information than the second law of thermodynamics, because the standard form of second law of thermodynamics just states that entropy production should be greater than zero. But here we have some more information, and this says that if you want to control the fluctuations, if you want to curb the fluctuations in heat engines, then like in power fluctuations, then you have to increase the entropy production. So entropy is a necessary evil in thermodynamics. You cannot escape it. Then these thermodynamic uncertainty relations can be translated to this inequality by using just putting the expression for this sigma, and by doing some algebraic step you can simply arrive at this inequality. Now I ask a question whether a heat engine can operate at Carnot efficiency at finite power. So the answer is yes, but at what cost? So if you put here eta equal to say eta c, so this will become 0, and then in order to satisfy this inequality, this relative power fluctuation, they should diverge. So although you can operate a heat engine with Carnot efficiency at finite power output, but with diverging power fluctuations. So this kind of heat engine is definitely not a useful heat engine. It is not a reliable heat engine. So now I will discuss thermodynamic uncertainty relation in major heat engines, and the talk is based on this paper. So back in 1959, so Scoville and co-authors, they showed that a major can be treated as a heat engine. So the efficiency, they showed that efficiency of a major is also limited by Carnot efficiency. So this is actually the very first model of quantum heat engine. And the idea is that you replace optical pumping with two thermal reservoirs. Okay, so here level G and 1 is connected to hot, hot reservoir. Level G and 0 is connected to the cold reservoir. And using these two reservoirs, you obtain the population inversion between these two upper levels. So now this engine is ready for the leasing action, and when you apply a semi-classical electromagnetic field, so it will stimulate transitions from level 1 to 0, and since this is due to the stimulated emission, these radiations, this will be in coherence with each other. So here power, as I mentioned, power mechanism in this heat engine is driven by this interaction Hamiltonian, and this is the total master equation. Like dynamics of this overall engine can be described by this master equation, where this LH and LC are the usual Lindblad form of dissipator for the thermal reservoirs, and these are simply jump operators. So I have written this dissipator for hot reservoir only, but we can similarly write the dissipator for cold reservoir as well. So now these equations can be exactly solved in a rotating frame. These are the equation, and these are the density matrix equation. So I just want to highlight that in this case, suppose we don't have the field in between these two levels, okay, then we can see that this in the absence of the field, these populations are coupled to populations only, and coherences are coupled to when lambda equal to 0, coherences only. So they are decoupled from each other. So here I want to actually compare thermodynamic uncertainty relation in two different configurations of this three-level measure heat engine. Both are known as SST heat engine in the literature, but I will show that actually these two both models, they yield different thermodynamic uncertainty relations and as well as different power. So where does this difference comes from? So I will discuss about that. So you can say that this is the first model. In the second model, I have just replaced this like cold reservoir is coupled to upper two level and this power mechanism is coupled to lower two level. Although they look alike, but there are differences. So so actually I have not showing any method. It can be calculated by using full counting statistics. So here are the results. So in the classical TUR relation, it says that this quantity, this should be greater than this, I will call it TUR ratio. It should be greater than 2. So we have plotted this ratio for now these two models. So for this model, I will call it model 1 and this is model 2. So we can see that in both models, for certain parameter regime, there are violations of thermodynamic uncertainty relations. So certainly this system measure heat engines, they can violate classical thermodynamic uncertainty relations. And we can also clearly see that in both cases, these TUR ratios, they are not equal to each other. Okay. And further, we also notice that the minimum of this ratio for model 1 is greater than for the model 2. So depending upon the parameter regime, one can outperform the other. So now where does this difference come from? So when we apply the high temperature limit, then both models yield same TUR relation. So this means that this is the analytical form. This means that if you ignore the spontaneous emission, because in the high temperature limit, you can ignore this term +1 as compared to NH. So you are ignoring spontaneous emission essentially. So then both models yield the same TUR relations. So this means that the difference was due to the quantum term spontaneous emission. Now, again in the high temperature limit, because these are all the positive constants and this is a square, so this is always smaller than 2. So interestingly, in the high temperature limit, it will always violate the thermodynamic uncertainty relations. And I think this might be due to neglecting the contribution from spontaneous emission, which is a quantum term. Okay, now I will discuss the thermodynamic uncertainty relation in measure heat engines. So in measure heat engines, like in 4-level measure heat engines. So now we have a bit exotic model in which we have replaced this upper level with 2 degenerate level. So now the effect of degeneracy in this upper level will be manifested in the form of the dissipator. So now in this dissipator, we will have this kind of cross terms, A1 row, these are the jump operators, A1 row, A2 dagger. So, and because of this, actually it will induce a coherence between these two degenerate levels, rho 1, 2. So we call it noise-induced coherence or vacuum-induced coherence. And actually, this can be quantified by a parameter P, which is actually angle between these two dipole transitions. So since there are now dipole transitions between these degenerate levels, 2G and 1G, so they are not distinguishable here because these are degenerate, so there will be certain kind of interference effect. So that interference effect gives rise to the noise-induced coherence term. So now, if you look at the master equation and density matrix equation, you can see that in the presence of noise-induced coherence or in the presence of degeneracy, now even in the absence of driving lambda equal to 0, these populations are coupled to coherences. So it has certain implication on the performance of the heat engine. So the question is whether you can exploit these effects to your advantage or not. The answer is yes. So here I have actually plotted the thermodynamic uncertainty relation, compared the thermodynamic uncertainty relation for these two models. Model 1, this one, 3-level heat engine and 4-level heat engine. So we check whether for the same entropy production, can you further suppress the relative power fluctuations for this degenerate heat engine. So actually the answer is yes, but not always. It depends upon what parameter you choose. So here I show that this solid curve is for the this TUR ratio for 3-level heat engine, and all these dash, dotted and dot dash curves are for 4-level heat engine with the noise-induced coherence for different values of noise-induced coherence parameter. So here I show that when you choose P equal to minus 0.95 or certain some other values as well, then it can outperform the 3-level counterpart. So if this means that we can use this noise-induced coherence, which is free, as a quantum resource to suppress the power fluctuations in heat engines. And in this plot, again, I have plotted this TUR ratio only for the 4-level heat engine for different values of driving. System path, system matter and system field driving for different values. So here we can see that this is plotted as a function of noise-induced coherence parameter P, and we can see that there is a minima always. Okay, but the main thing is that when it approaches P equal to 1, the complete constructive interference, then these fluctuations diverges. So we should not operate our heat engine at exactly P equal to 1 value. So actually there are certain papers by Saclay and their group which showed that at P equal to 1 the power will be doubled. But here we can conclude that then these power fluctuations will also amplify and they will diverge. So you should not operate heat engine at P equal to 1 but just a slightly lower value of noise induced coherence parameter. So here are some analytical observation. When you put P equal to -1, then you always satisfy thermodynamic uncertainty relations. And in the high temperature limit, if you subject the heat engine to high temperature limit, this TUR ratio is always equal to 2. So it satisfies the equality. Okay, so again in this histogram we have here the sampled value of this all TUR ratios for all models Q1 and this 4-level model, model 1, model 2 and 4-level model for random sampling over a region of parameter space, and in this inset we have plotted the subset of the data for which there is violations of this standard thermodynamic uncertainty relation. So in all cases we can say that there is violations, but most of the values actually lies close to 2. For most of the events the value lies quite close to the ratio. So here is the conclusion. So classical thermodynamic uncertainty relations, they can be violated in major heat engines. Then spontaneous emission plays an important role in the degree of violations because we have shown that in the high temperature limit both models yield the same TUR. And again in the high temperature limit classical TUR is always violated for these 3-level major heat engines. And depending upon the parameter regime of operation, this phenomenon of noise induced coherence can be exploited in our advantage, and you can suppress the relative power fluctuations. So this was my current work. So right now actually I am working on exactly, I want to evaluate the contribution from coherences, coherence term from in this thermodynamic uncertainty relations. For that we have to go beyond the steady state, and for that quantum trajectory approach may be employed. Okay, thank you.
Okay, thank you for this talk. So please questions.
So Varinder, I don't know if you are aware of this paper where we have like one ground state and then multiple degenerate excited states.
Okay.
And then we did synchronization of those kinds of atoms, right? So now not to talk about synchronization per se, but if you extend your degenerate space
Yes.
to much larger n minus 1, how
Okay.
does this scale with n?
I think, okay,
Because you have a coherence advantage, right?
Okay.
Because your noise induced,
yes,
it's inducing coherence. So
but for now my intuition says that it will not affect it much because the coherence will be shared among all the levels, equally shared, because if there is exact degeneracy.
L1 norm of coherence increases with the number of atoms.
Yes, yeah, the
with the
norm,
inverse space dimension.
yes.
The absolute value of it.
Okay,
So
maybe
you might-
then I will check it.
I mean,
to
to
now
put
I
it
was
physically,
okay.
if the work that is, if the work that I'm thinking of, the work output is basically that I go from level excited state to ground state and emit light.
Yes.
Having many more excited states improves the light that comes out.
Okay.
So
Because it is coupling to a lot of models. So if you
lots of modes basically.
Yeah, lots of modes. Yeah, this degenerate modes.
Depends on what it couples to. But
Yes.
yeah.
So maybe I should check this.
What we had found was that the phase itself has a synchronous behavior of the off diagonals of the.
Okay.
But anyway, yeah, just a thought. Yeah.
Okay. Thank you.
So any more questions? So if there are no more questions, then let us thank Varinder again. And